Your smartphone, your car's engine, and the world's most advanced microchips all share a secret heartbeat, a brittle crystal that breathes. To truly understand the trajectory of modern technological advancement, one must first examine a phenomenon that appears to blur the line between mechanical reality and electrical magic. At the very heart of this intersection is the piezoelectric effect, a physical property whose name is derived from the ancient Greek word piezein, meaning to press or to squeeze. When certain crystalline materials are subjected to physical, mechanical stress, they spontaneously generate an electrical charge. This behavior is not an act of alchemy, but rather a profound manifestation of atomic architecture. In a resting state, the positive and negative charge centers within these highly structured asymmetrical crystal lattices perfectly overlap one another. Because these charges cancel each other out, the material maintains a balanced electrical state, resulting in a dipole moment of exactly zero. However, the moment a mechanical force is applied to the material, the crystal lattice physically deforms. This deformation forces the internal charge centers to shift relative to one another, directing negative charges to one side of the material and positive charges to the opposite side. This instantaneous shift breaks the electrical balance, generating an electric dipole moment and a macroscopic potential difference across the crystal. To illustrate the sheer, concentrated magnitude of this energy conversion, a simple 1 cubic centimeter cube of quartz subjected to 2 kilonewtons of correctly applied physical force can generate an astonishing 12,500 volts of electricity. This highly localized generation of high voltage from a simple mechanical squeeze is best observed in the commonplace mechanism of a portable piezo gas lighter. Hidden within the plastic casing of a standard handheld lighter lies a marvel of mechanical engineering, a miniature spring-loaded hammer mechanism, and a highly engineered crystal, typically made of synthetic ceramics like lead zirconate titanate or PZT, or sometimes natural quartz. When the user presses the thumb trigger, they are not directly sparking a flame. Instead, they are loading kinetic energy into a stiff inner spring. As the push button travels downward, mechanical tension continues to build within the spring assembly until it reaches a critical threshold. At this exact point, the resistance of the internal wall is overcome, releasing the hammer to strike the top of the piezoelectric crystal with sudden, concentrated force. This instantaneous, forceful physical deformation forces the atomic lattice of the crystal to violently compress. The shifting atomic charges create an immediate voltage spike that is captured by a metallic end cap and routed through a thin metal wire to an ignition head near the gas nozzle. In a fraction of a second, the kinetic energy of a human thumb is transformed into a 7,000-volt electrical arc that jumps across the air gap, igniting the rapidly escaping air-gas mixture. It is a violent, elegant translation of energy that happens seamlessly, entirely devoid of external batteries or electrical connections. The scientific discovery of this invisible interaction dates back to the late 19th century. In 1880, two young French physicists, brothers Pierre and Jacques Curie, built upon the existing scientific knowledge of pyroelectricity, the generation of an electrical charge resulting from extreme temperature changes in a crystal. The Curie brothers hypothesized that a mechanical equivalent to this phenomenon must exist. Utilizing a rudimentary set of tools consisting of nothing more than tinfoil, glue, conductive wires, simple magnets, and a jeweler's saw, the Curie brothers meticulously prepared and tested various crystalline structures. They applied physical pressure to crystals of tourmaline, topaz, cane sugar, quartz, and Rochelle salt, conclusively measuring the appearance of surface charges. Their initial demonstrations proved that quartz and Rochelle salt exhibited the most dramatic and reliable piezoelectric capabilities of their era. Shortly thereafter, in 1881, the physicist Gabriel Lippmann mathematically deduced from fundamental thermodynamic principles that this effect must be completely reversible. The Curie brothers immediately confirmed the inverse piezoelectric effect, proving that applying an electrical field to these very same crystals caused them to physically deform and change shape. This revelation laid the theoretical groundwork for bridging the gap between the physical and digital worlds, a translation best exemplified by the early phonograph. For decades, the phonograph needle, or stylus, served as the primary interface between the physical topography of a vinyl record and the human ear. Early phono cartridges heavily relied on Rochelle salt because of their intense piezoelectric sensitivity. The surface of a vinyl record is essentially a microscopic canyon featuring undulating grooves that encode complex audio channels. As the turntable spins, the stylus acts as an explorer, dragging through these microscopic winding grooves. The massive inertia of the tone arm keeps the heavy cartridge assembly steady, allowing the ultralight needle to move freely and track every microscopic bump and curve of the groove. These rapid microscopic physical vibrations are directly transferred upward into the cartridge, systematically squeezing and stressing the delicate Rochelle salt. As the crystal flexes under the mechanical strain, it generates a fluctuating electrical voltage that perfectly mirrors the physical shape of the groove. This continuously alternating current can then be fed into an amplifier and projected through a speaker as audible sound. The phonograph cartridge acted as a profound electrochemical translator, proving to the general public that an invisible, highly structured interaction within a mineral could seamlessly map physical topography into continuous, high-fidelity electrical audio data. The translation of mechanical strain into electrical signals remained largely confined to laboratory curiosities and acoustic novelties until the brutal geopolitical realities of the First World War forced a rapid evolution. The advent of the German U-boat presented an unprecedented and terrifying threat to Allied naval and merchant fleets. Submarines operated entirely in the invisible high-pressure domain beneath the ocean's surface, rendering traditional optical tracking useless. Echolocation, or the use of reflected sound waves to detect submerged objects, had been theorized by scientists, but executing it practically required generating highly directional sound waves. The French government commissioned the physicist Paul Langevin to develop a system capable of actively spotting submerged submarines. Langevin intimately understood the physics of sound. He knew that lower-frequency sound waves propagate outward in all directions, making them useless for pinpointing a specific target. To create a narrow, directional beam of sound that would act like an acoustic searchlight underwater, the transmitting source needed to generate high-frequency ultrasonic waves. Furthermore, to maintain this tight beam, the physical diameter of the sound source had to be at least 5 times the wavelength of the sound in seawater.
Langevin early attempts to generate these directional waves in 1915 were fraught with extreme engineering struggles. Working alongside Russian engineer Konstantin Chelyabinsk, Langevin initially developed a device known as a singing condenser. This early electrostatic projector utilized a remarkably thin 1 micrometer sheet of mica acting as a dielectric in a vacuum, placed directly against a metal sheet. The objective was to create ultrasonic waves using an experimental arc transmitter, but the system was plagued by catastrophic failures. The intense high-voltage electricity required to generate the sound consistently arced and sparked straight through the fragile mica film, destroying the transmitter. Furthermore, the carbon granule hydrophones they attempted to use as acoustic receivers were easily overwhelmed. The deafening hydrostatic noise generated by the turbulent, high-pressure oceanic environment drowned out any faint echoes reflecting off a submarine. Seeking a much more robust active medium, Langevin turned to the piezoelectric properties of natural quartz in 1917, seeking to exploit the material's unique ability to simultaneously generate ultrasonic pulses through the inverse effect and receive them through the direct effect. However, manipulating natural quartz for underwater submarine detection introduced a severe paradox of scale and physics. To maximize the operational range of the sonar unit to practical combat distances, Langevin needed to lower the acoustic frequency from 100 kHz to 40 kHz because higher frequencies were rapidly absorbed by thermoviscous effects in the cold seawater. By dropping the frequency to 40 kHz, he calculated he could increase the detection range 6-fold. Yet, the strict physical laws of piezoelectric resonance dictated that the quartz crystal would achieve its primary resonance vibrations only when its thickness was exactly half the wavelength of the sound wave passing through the elastic medium of the crystal itself. At 40 kHz, this equation required a solid slice of natural quartz thicker than 50 millimeters and massive enough in diameter to maintain the directional beam. Single, flawless, natural quartz crystals of such massive dimensions were exceptionally rare, heavily brittle, and virtually impossible to source in the massive quantities required to outfit a wartime naval fleet. Furthermore, increasing the diameter of the transducer to match the lower frequency meant the overall mass of the quartz would scale inversely with the cube of the frequency, resulting in impossibly heavy, unwieldy equipment that would tear itself apart under its own mechanical vibrations. Faced with the strict limitations of natural geology, Langevin engineered a brilliantly deceptive solution, the quartz sandwich transducer. Rather than relying on a massive single block of impossibly rare quartz, Langevin bonded a remarkably thin 4mm slice of X-cut quartz directly between two heavy 3-centimeter thick plates of steel. This mosaic assembly acted as a single, unified harmonic oscillator. The resonant frequency was no longer dictated by the thickness of the quartz alone, but rather by the combined acoustic mass and elasticity of the entire steel-quartz-steel composite structure. This ingenious design allowed the transducer to operate effectively at the lower 40 kHz frequency without requiring giant natural crystals. By the summer of 1918, a prototype of this active sonar unit, housed in a protective canvas dome to shield it from turbulent waters, was secretly tested aboard a shallow water trawler operating at 15 knots off the coast of Toulon, France. The results were staggering. Langevin's piezoelectric array successfully achieved an effective underwater echo detection range of more than 2.7 kilometers. The heavy steel plates protected the delicate quartz interior from the crushing hydrostatic pressures of the deep ocean, while the quartz served as the tireless engine of the machine. The crystal converted the ship's massive electrical pulses into violent mechanical acoustic waves and instantly reverted to a highly sensitive receiver to translate the faint returning mechanical echoes of a submarine back into readable electrical signals. Langevin's wartime breakthrough permanently altered humanity's relationship with the ocean, proving that mechanical pressure and synthetic acoustic engineering could be wielded to map the invisible world. This singular invention birthed the era of modern ultrasonics, laying the foundation for everything from modern naval navigation to non-invasive medical scanning technologies. While the quartz sandwich transducer successfully proved the viability of piezoelectric engineering on an industrial scale, natural crystals possessed inherent physical limitations that prevented broader mass adoption. Materials like Rochelle salt were incredibly sensitive to mechanical stress, but they were highly susceptible to environmental degradation. They rapidly absorbed moisture, dissolved in high humidity, and completely lost their piezoelectric properties when exposed to high heat. Quartz, while structurally stable, produced a relatively weak piezoelectric response and was notoriously difficult to cut and shape into complex geometries. The relentless global demand for advanced sonar systems, sensitive microphones, and ignition devices through the Second World War pushed researchers away from relying on natural geology and towards synthetic creation of ferroelectric ceramics.
The monumental turning point in this material evolution occurred around 1952, when scientists operating out of the Tokyo Institute of Technology successfully developed lead zirconiate titanate, universally known in the engineering world as PZT. PZT represented an astronomical leap in materials science. Unlike natural quartz, PZT is a metallic oxide-based piezoceramic composed of lead and zirconium elements fused with a titanate compound. When these high-purity precursors are mixed and fired, the material undergoes a radical structural transformation, assuming what is known as a perovskite crystal structure. The specific architecture of the perovskite lattice is the secret to PZT's immense power. To visualize this, imagine each microscopic unit cell of the crystal as a rigid, cage-like lattice of large divalent metal ions, primarily lead. Trapped inside this atomic cage is a much smaller tetravalent metal ion, typically titanium or zirconium. When the ceramic cools below its Curie temperature, the crystal lattice naturally distorts into a tetraagonal or rhombohedral symmetry. This distortion forces the central positive ion slightly off-center within its cage, creating a built-in, permanent electric dipole moment within every microscopic domain of the solid ceramic. The true revolutionary power of PZT was that it was an engineered compound rather than a mined mineral. Because it was manufactured, its electrical and mechanical properties could be explicitly tuned by human engineers to meet precise specifications. By strictly adjusting the ratio of zirconia to titania, or by doping the raw powder with secondary materials, manufacturers could fundamentally alter the ceramic's electromechanical behavior. The industry quickly bifurcated into two primary material classifications. Soft PZT was engineered to possess extreme charge sensitivity, a fine grain structure, and a high dielectric constant. This made soft PZT ideal for delicate applications where receiving incredibly faint signals was critical, such as in aerospace non-destructive testing devices, sensitive flow meters, and precise medical ultrasound probes. Conversely, hard PZT was explicitly engineered with a higher mechanical quality factor and low dissipation. This meant it could withstand severe mechanical stress and resist heat generation, making it the absolute backbone of high-power industrial applications. Hard PZT drove massive ultrasonic industrial cleaners and advanced deep-water military sonar arrays that needed to operate continuously without succumbing to thermal degradation. Furthermore, the highly meticulous manufacturing process of PZT allowed it to be molded into virtually any conceivable shape. The production of PZT powder involves 6 distinct and heavily controlled operations. After high-purity raw materials are evaluated, they are precisely weighed and wet-milled together to achieve a uniform particle size. The material is then calcined in high-purity crucibles at temperatures reaching 1,000 degrees Celsius to form the desired PZT phase. Because lead oxide is highly volatile and hazardous, proprietary measures are taken during this firing process to prevent lead evaporation from altering the chemical composition. After calcining, an organic binding agent is added to the slurry, which is then fed into a massive spray dryer. As the water evaporates, the machine produces perfectly uniform, microscopic, free-flowing hollow spheres of PZT. Finally, these hollow spheres are injected into custom dies and dry-pressed under an incredible 10,000 pounds per square inch of force. This massive pressure crushes the hollow spheres into closely packed crystallites, ensuring that any trapped air escapes and forming lamination-free green ceramic shapes before their final sintering. This absolute mastery over synthetic ceramic formulation precipitated a massive shift in how the piezoelectric effect was deployed globally. For decades, the primary application of the technology had been the direct effect, passively squeezing a crystal to receive an electrical signal, as seen in phonograph needles and early underwater hydrophones. With the advent of PZT, engineers pivoted aggressively to harnessing the inverse piezoelectric effect with unparalleled precision. By applying a controlled electrical field to a polarized PZT ceramic, the billions of microscopic dipoles trapped within the perovskite lattice are forced to align and physically elongate. This forces the entire ceramic structure to mechanically deform and expand. Because this mechanical expansion is entirely a solid-state phenomenon, free from traditional gears, lubricants, bearings, or sliding moving parts, the movement is instantaneous, incredibly forceful, and flawlessly repeatable. This marked the dawn of the true actuator era. Synthetic piezoelectricity transitioned from being a passive listener into an active, aggressive driver of physical motion, providing the foundational architecture for the precise, controlled movements required by late 20th century industrialization. By the early 21st century, the ability to dictate mechanical movement via the inverse piezoelectric effect has become the absolute cornerstone of high-tech automated manufacturing. As technological progression demanded the relentless miniaturization of electronics, traditional mechanical motors and lubricated drives became entirely obsolete for microscopic tasks. Standard motors were far too slow, generated excessive thermal friction, and were plagued by mechanical backlash that ruined tight microscopic tolerances. Piezoceramic actuators operating entirely as solid-state phenomena driven by atomic distortion replaced them entirely,
defining the architecture of modern precision.
Nowhere is this extreme physical precision more critical than in semiconductor manufacturing and modern DUV and EUV lithography. The creation of modern computer microchips requires projecting impossibly dense, nanoscale circuit patterns onto 300mm silicon wafers. To achieve the necessary feature verification and alignment, the heavy wafer chucks holding the silicon must be positioned with sub-nanometer resolution. Multi-axis piezoelectric positioning stages serve as the beating heart of these lithography tools. Because piezo actuators manipulate heavy objects by applying voltage directly to a PZT lattice, they generate a fractional coupling force of tens of newtons, providing incredibly high force movement with zero internal friction and absolutely no backlash. To overcome the natural crystalline tendencies of material creep and hysteresis, modern piezo nano-positioners integrate high-resolution feedback measurement sensors and advanced closed-loop controllers, guaranteeing flawless linearity and perfect repeatability. In the ultra-high vacuum environments required for manipulating delicate electron beams and growing pristine epitaxial layers on wafers, traditional liquid lubricants would immediately outgas, boil off, and destroy the sterile cleanroom atmosphere. Ultrasonic piezo motors, however, operate seamlessly in a vacuum. They can hold a precise position indefinitely without any positional drift and without consuming continuous power, allowing multi-million-dollar lithography tools to align payloads weighing up to 20 kilograms with atomic-level precision. Beyond lithography, piezo actuators are deployed to apply a perfectly constant pressure onto wafer surfaces during the physical polishing phase to prevent micro-warpage, actuate chemical vapor deposition valves to ensure gaseous chemical films are deposited as thinly as possible, and generate the precise ultrasonic frequencies required to physically bond fine gold wires to the connection points on finished microchips. This solid-state reliability is equally transformative in the violent, high-temperature, high-pressure environment of the modern internal combustion engine. High-efficiency diesel and gasoline direct injection systems have fundamentally abandoned traditional electromagnetic solenoid injectors in favor of advanced piezoelectric fuel injectors. A conventional solenoid injector relies on magnetism to pull a valve open. This process requires roughly 200 to 300 microseconds to generate a magnetic field and physically complete the movement. In the context of an engine rotating thousands of times per minute, 300 microseconds is an eternity, severely limiting the engine to 1 or 2 clunky fuel injections per combustion cycle. Piezo injectors, however, react almost instantly to an electrical pulse. The engineering behind a piezo injector is a masterpiece of hydraulic and mechanical amplification. The physical expansion of a single PZT crystal under a safe automotive voltage is microscopic. A slice of piezo material 0.02 of an inch thick expands by a mere 0.00002 inches when struck with 140 volts of electricity. To generate usable macroscopic movement, engineers stack hundreds of extremely thin piezoelectric slices on top of one another within the narrow injector body. When the engine's computer calls for fuel, voltage is applied and the entire stack expands simultaneously, achieving a total cumulative movement of approximately 0.004 inches. While this movement is directed downward as the stack expands, a system of microscopic internal levers or a complex hydraulic amplification chamber instantly reverses and amplifies the force, violently lifting the injector's sealing pintle needle. This frictionless, lightning-fast actuation allows the nozzle to open and close multiple times within a single microscopic combustion cycle. By dividing the fuel delivery into a highly calculated series of pre-injections, main injections, and post-injections, the piezo injector perfectly optimizes the air-fuel mixture within the cylinder. This unparalleled precision smooths the violence of the combustion event, drastically improving throttle response, reducing engine vibration, maximizing fuel economy, and vastly decreasing the emission of unburned hydrocarbons and toxic nitrogen oxides. Furthermore, because the physical expansion is based purely on the crystalline lattice stretching rather than metal sliding against metal, piezo injectors operate with extreme durability, easily overcoming fuel pressures exceeding an incredible 30,000 pounds per square inch. The mass deployment of piezoelectricity in everything from semiconductor lithography to automotive fuel injection highlights a broader industrial truth. The modern automated manufacturing line requires mechanical components that simply do not fatigue. Whether firing highly pressurized fuel into a cylinder thousands of times per minute, guiding a cutting laser, or driving ultrasonic wire bonding to attach microscopic wires to integrated circuits, the piezoelectric effect has established an infrastructure of extreme, unyielding reliability. The capability to translate simple electrical commands into exact sub-nanometer physical outputs has cemented the inverse piezoelectric effect as the indispensable pulse of global manufacturing. As the timeline progresses into the cutting edge of 2026, the trajectory of piezoelectric technology is undergoing yet another profound global inversion. If the 20th century was defined by using mechanical strain to generate listening signals, and the early 21st century was defined by using massive electrical power to drive precise mechanical movement, the current era is entirely defined by utilizing advanced nanotechnology to passively harvest the ambient mechanical energy of the world. The rapid proliferation of the Internet of Things and the global demand for autonomous distributed sensor networks have exposed the critical vulnerability of traditional chemical batteries. Batteries are inherently toxic, bulky, require constant replacement, and possess severely limited lifespans. The ultimate solution has emerged in the form of piezoelectric nanogenerators and triboelectric nanogenerators. These sophisticated nanogenerators are engineered to passively scavenge wasted kinetic energy from the surrounding human environment and directly transduce it into usable electrical power. On a macroscopic scale, this takes the form of radically redesigned smart infrastructure. Civil engineers are actively embedding robust, large-scale piezoelectric arrays directly into the asphalt of busy highways, the concrete of pedestrian pavements, and the floors of heavy transit hubs like airports. As thousands of multi-ton vehicles and human footsteps continuously compress these embedded ceramics daily, the massive mechanical load is captured and converted into grid-scale electricity. This harvested energy is immediately routed to power local streetlights, illuminate airport terminals, and sustain structural health monitoring sensors embedded deeply in bridges, creating self-sustaining urban ecosystems that thrive purely on the sheer kinetic chaos of human transportation.
However, the most intimate and transformative application of energy harvesting in 2026 lies in the medical sector, specifically through the advent of self-powered wearable health monitoring systems and implantable therapeutics. Early wearable electronics were severely hindered by rigid substrates and hazardous battery chemistries that caused immense environmental waste and patient discomfort. Modern bioelectronics have resolved this bottleneck by synthesizing biodegradable and highly biocompatible piezoelectric materials, with silk fibrone currently leading the biomedical revolution. Unmodified silk fibrone exhibits inherent piezoelectric properties due to its highly anisotropic molecular structure, specifically the non-centrosymmetric anti-parallel beta sheet microcrystalline domains that naturally form a local dipole matrix. When a patient wearing a silk fibrone sensor moves, basic muscle contractions and simple knuckle bending apply mechanical shear deformation directly to the protein lattice. This microscopic lattice displacement triggers charge separation, generating an electrical signal that simultaneously powers the device and provides real-time, high-fidelity physiological data, such as electrocardiography and respiration metrics, without ever relying on an external power source. Because silk is completely biocompatible and degrades safely in alkaline conditions over a highly predictable time frame of 8 to 20 weeks, these wearable sensors completely eliminate the burden of electronic medical waste. Internally, piezoelectricity is actively revolutionizing regenerative medicine and precision drug delivery. The healing of severe joint degradation, such as osteoarthritis, has historically relied on highly invasive scaffolds or external ultrasound activation that complicates clinical application. In 2026, medical researchers deploy biodegradable piezoelectric triboelectric nanogenerator patches directly into degraded joints via minimally invasive surgical procedures. Measuring a mere 5 by 5 by 1.5 millimeters, these hierarchical microstructured patches harness the patient's natural endogenous joint movement. As the patient simply walks, the mechanical friction and physical compression of the joint stimulate the piezoelectric triboelectric nanogenerator patch, generating a massive localized surface charge density of up to 84 microcoulombs per square meter directly in vivo. This continuous, self-generated electrical biostimulation directly mirrors the body's natural strain-generated potentials. The electricity significantly accelerates calcium ion influx, upregulates chondrogenic gene expression, and actively promotes bone marrow stem cell migration to the injury site. The result is a drastic reduction in painful osteophyte formation and the active regeneration of articular cartilage, powered entirely by the patient's own kinetic walking motion. Once the therapeutic remodeling phase is fully complete, the piezo tag patch simply and safely degrades into the body within 15 to 60 days, requiring no secondary surgical explantation. Simultaneously, active transdermal patches use similar piezoelectric actuators to gently disrupt the stratum corneum barrier of the human skin. Instead of relying purely on the passive chemical diffusion of traditional patches, programmable microactuators utilize the inverse piezo effect to drive iontophoresis or vibrate microscopic microneedle arrays. This ensures sustained, on-demand drug delivery into the bloodstream that is actively triggered by the patient's thermal or mechanical health metrics. The incredible journey of piezoelectricity is a perfect testament to humanity's relentless desire to manipulate the atomic fabric of the physical universe. What began in 1880 as an obscure scientific parlor trick involving tinfoil, weights, and Rochelle salt has systematically redefined the absolute boundaries of physics and engineering. From the high-pressure oceanic depths of World War I, where quartz arrays first allowed navies to map the invisible underwater world, to the mid-century ceramic revolution that introduced synthetic, tunable perovskite lattices, piezoelectric materials have constantly evolved. Today, they stand as the supreme architects of modern precision, effortlessly moving silicon wafers by fractions of a nanometer in a vacuum and firing high-pressure fuel into combustion chambers in microseconds. As global society confidently transitions into an era of self-powered biomedical devices and energy-harvesting smart cities, the astonishingly simple act of squeezing a crystal remains the indispensable, invisible pulse driving the entire global high-tech economy.